record, draw. I'm going to go back to orange. Okay. So when I put the diode in series with between the input and the output, this is a rectifier. These are the two basic types. And I am recording. And if I put let's do this one. If I put the diode in parallel between V out and ground, this is a limiter. So we want to look at how these respond to a sine wave. So for the rectifier, the one I picked, we've got two conditions here. The input voltage, which was right here, Vn could be greater than 0.7 and Vn could be less than 0.7. Now, if Vn is greater than 0.7, the diode will be on. And that means that it's going to act like this. This is Vn. It will be a 0.7 of a volt battery. A positive goes the other way. Yeah. Like this, positive minus 0.7 volts into a resistor. We've got V out. So if I write a KCL equation across here, Vn minus 0.7 of a volt will equal V out, or V out, yeah, that's V out will equal Vn minus 0.7. Right. Now we look at the other case, something bright. Oh, it's an ugly green. If Vn's less than 0.7 of a volt, the diode is off. And get some practice with these. And then what I can say is basically it's an open circuit. And V out is going to equal whatever the voltage is across that resistor with nothing going into it. So V out equals 0. And I could plot this if I had an input sinusoid, something that looked like this, that went up to 10 volts and goes down to minus 10 volts. What I would have is I'd have two regions of operation here. Two basic things that could go wrong. The most I could get out of this with this peak 10 volt sine wave, my max would be 9.3 volts. And my min here would be 0. So it would follow along pretty much with the sine wave until we got to about there. And every place where Vn was less than 0.7 of a volt, I get 0 out. I get something that looks like this. And this is my V out curve. And the green one is my Vn curve. And I know what the min and the max are. With the limiter, we could go through the same operations here. Basically, there's going to be three different conditions here. Vn's less than negative 0.7. Vn is greater than positive 0.7. And then Vn's in the middle. Vn is greater than 0.7, negative 0.7. Oh, in there. And it's less than positive 0.7. So we got three different conditions here. If it's less than 0.7, then negative 0.7, then D2 is going to kick on. And the other diode will be off. And I'm going to get my V out will equal 0.7. We did a lab like this. So we did spend a lot of time on this. If Vn is greater than 0.7, then D1 kicks on, and V out will equal 0.7. And if it's in between, both the diodes are off. So Vn is just going to equal V out. It just passes through a resistor with no current. So if I want to draw that and I have the same input sine wave, let's change the color to black here. What I'm going to get is something that it'll go up to 0.7. It'll go down to negative 0.7 volts. And it's going to max out there, and it will follow the sine wave when it's not in there. And this is called a whatchamajigger. It's called a limiter. I wrote that down. Okay. So good thing to look at. What else do we have going on here? Small signal circuits with diodes. You pretty much have to make the assumption that the diodes are on or off. If I have positive voltage on the positive side of the diode, which is right here, and a smaller voltage on the negative side, I'm going to guess that it's on. And same thing here, I got a positive voltage here. I've got a more negative voltage down there, so I'm going to say both of them are on. And then I could replace them. Replace the diode with a 0.7 of a volt source. This would be a 0.7 of a volt source. And now we can start figuring out what the voltages and currents are in this circuit. I don't know the currents. I do know the voltages across the diodes. One side of the diode's tied to ground. So if I go 0.7 of a volt above it, this will be 0.7. And if I go 0.7 of a volt below this, this will be at 0 volts. Now that I have the voltages across the resistors, I can calculate their currents. So look for the things that you know solidly and don't try to guess first. So for R4, IR4 is going to equal its voltage drop, which is 3 minus 0.7 over 1K. So that should be 2.3 milliamps. That is a good sign. Those diodes are on too. For R5, the voltage at the high side is 0. So IR5 is going to be 0 minus -3 over 2K. So that will be positive 1.5 milliamps. Because this is the high side of the resistor. So we've got IR5, and then we can use KCL to find ID5. So ID5 plus IR5, this is my KCL equation, plus IR5 equals IR4. And we've got 2 of those, so ID5 will equal 2.3 minus 1.5 is 0.8 milliamps. 8 milliamps. All right. We've got all the voltages and currents. If we wanted to do a small signal model of this, remember the small signal model of a diode is just a resistor. And the resistance value is, VT over its current. So RD5 would be VT over its current. Yeah, I got that right. ID5. Now we can do that calculation. VT is written on the very front of the final exam. It says it's 25.9 millivolts. So I'm going to use that. Millivolts. ID5 was 0.8 milliamps. So that will, I got to change colors, or I can't draw on the purple. That is going to equal 32.4 ohms. That's pretty much all we did with the small signal model of a diode. So I think there's one diode problem on the exam. One or the other, something like that. Semiconductor physics, we did a lot on exam 2, so maybe not so much on the final. The basic equation for the current through a diode, good thing to have on your note sheet. You can also solve that for VD and be able to solve that if you know any of the variables. It says exam 3 and 4, that's old. There were semiconductor physics problems on the exam 2. I think we used this equation, and this equation. And qualitatively, I asked you a multiple choice question, I think, about that equation and as it compares to the depletion width also. That was probably a little bit, everybody missed that. Okay, and then we get into MOSFETs. 2 MOSFET problems, at least 2. What did I do? Oh my gosh. There are so many possibilities for this class. What the heck did I do in MOSFETs? Let me read the final to you eventually. Oh, I didn't do that. Oh, don't worry, I'll get you in. I'll get you in back in 380. Okay, so there's 2 MOSFET problems on the exam. You got this on exam 2. If it's NMOS, can you look at the picture of the device and tell me which is the drain and which is the gate and which is the source? Can you calculate VDS, VGS, and then later on ID? Figure out, use the little algorithms, either one of these, to figure out what operating region it's in, and then calculate the current. So that's the idea. Get trickier versions of this when we get to 380, because I'll add in things like the channel length modulation and the body effect. It's not so bad. PMOS, same thing. So that's a good thing to go back and review. When I'm doing the small signal model, this is for a MOSFET. There's 2 parameters in here that I have to calculate, and I calculate these from the DC values. So there's GM and there's little RO. The formula for little GM, if you know KN, you can use any 3 of these formulas and they will come out to be the same answer. If you don't know KN, you have to use this formula. If you don't know the drain current, you have to use that formula. If you don't know the over voltage, you have to use that formula or this formula. So all 4 versions of that formula are good things to know. Same thing with RO. There are 2 different versions of the formula. One looks like 1 over lambda ID, where lambda is in per volts. And there is one with the early voltage, where the early voltage is in volts. So depending upon what you're given, you can calculate both of those. This is the model. The gate, whatever's tied to the gate in your circuit goes here, whatever's tied to the source goes here, whatever's tied to the drain goes there. Okay. We have plenty of time. Yeah, that should have gone later for some reason. I think I did them in the order I did the slides. Okay. For inverters, a lot of this stuff, we are going to nail this in 380. We're going to do labs. We're going to measure it. You did some of that in here, but I'm probably not going to put that on the exam because that's a little bit more than what we learned in an introductory course. This is a big deal equation right here. It's one that people out in the industry and all over every place use to kind of talk about how we're going to get the heat out of the circuit. Heat is a major deal, and we hardly talk about it in school unless you listen to me, talk about blowing things up. Too much power and you burn something up. So we want to limit the power. And the three main things we can do to limit power is lower the frequency, lower the load capacitance, make our transistors smaller, or lower VDD. So that is, yeah, something to think about and ponder. I love that equation. Delays, this is another one we're going to spend a lot of time on. It's like this is the first two labs in 380. There'll be lab quizzes on this and all kinds of things. So I'm not going to worry as much about taking care of this on the final exam. This is something fundamental. This is something I really care about, is being able to draw these CMOS circuits. Now, if I look at this, remember our parallel, our NMOS. I always do the NMOS first. Parallel is ORs. Series is and then I put a bar over the whole thing because when that function's true, it's going to pull the output low. Invert the result. Okay, so I'm looking at this one right here. I have B in parallel with C. So that is B or C. It's ANDed with A. And then that is in parallel with the series combination of B and E. What happened? And then I put a bar over the whole thing. So that's the function right there. I think on exam 1, I asked you to do, exam 2, sorry. I asked you to do a partial circuit and tell me what the function was. On the final, there will be another one of these. Most of you got it right, but some of you didn't, so you get to. Now, if I give you something like this, Q, it's A or B, C, D, whatever that says. I'm going to have to draw a circuit for that. So D and E are in parallel. I do the NMOS first. D, because it's D or E. That's a really sloppy transistor. D or E. And that gets ANDed with the series combination of B and C. B, C. And if A is true, the whole function's true, so I have to put A in parallel. And this would be my Y. And I'll draw the PMOS part of that circuit over here. I was hoping to use that for something else. The PMOS version of this is A was in parallel with the whole thing, so A's got to be in series with the whole thing. Oh, I know what I did. It's in series. These three legs are in series, B, C, and D, E. So I have 3 branches in parallel. B. Notice that these are all grounded. It doesn't work if it's not grounded. A. Oh, I know what I did. Oh, well, I'll just go ahead and finish this like this. D, E. They were in series, and that goes to VDD. You need power to make this work too. whatchamacallit, see, the bubble says it's PMOS. A bubble or an arrow is good enough to indicate it's PMOS. Oh, good. And this goes back to Y. What am I looking for? Yes. You have to come, you can either come pick up your exam or you send me an email saying you want a copy of it. You've got to ask for it. I'm not going to just send them out to everybody. Okay. That would take me like all day. Now, if I have something that looks like this, let's say I had, let's swap color. I'm going off topic a little bit. Let's say I had something, a function that I wanted to draw that was like z equals a or b. Let's do something simple. Well, I don't have the bar and the structure is going to invert it. So what I need to do here is I need to put a double bar over the top. Any other method than this leads to extra transistors, which tend to upset me because they take up more room. So this is A bar. We use De Morgan's theorem, and we get A bar and B bar bar. So the function we draw there would be an and. I'm just going to do the end loss of this. A bar and B bar would be the inputs. And then we would have to do a parallel on the PMOS. So that's about everything we did so far with digital CMOS. This is a common source amplifier. We didn't get to this on exam 2. Maybe something like this on the final. There were steps here, what we need to do. We need to start by drawing. Did I do this step? Yes. Oh, thank goodness. Okay, so I don't have to draw so much. Draw the DC equivalent circuit. Next step is to find the Q point. That's the DC operating point. Big things we need for that are VDS, VGS, and ID. Because we need those to calculate GM and R naught. And then draw the AC equivalent circuit, include GM and R naught, and then we're going to divide the circuit into 2 parts, find VGS over VN and VGS over. That's identical. We find VGS over VN. We found the other thing here should say V out over VGS. We multiply those 2 together and we get V out over VN. And V out over VN is the gain of the amplifier. So the first step is to draw the DC circuit. And remember, for DC circuits, capacitors are shorts. There are no inductors, they don't exist. Capacitors are shorts. And DC voltage supplies get shorted out. Short. Shot. I can't spell it all today. Shorted out. DC current supplies become opens. So we're looking at this circuit right here. Oh, wait, that's wrong. I should read AC. I'm getting tired. What is this thing doing? This is the AC voltages should be shorted, and the AC current sources are open. That's for the DC circuits. So we short this capacitor out. We short out the AC voltage source, and we short out this capacitor, and we short out this. Wait, that is completely wrong. Thank you. Sorry, let's start this up. Let's start this problem over again. The caps opens. I was thinking, I know what I was thinking. I was thinking AC when I wrote this. The caps are open. So that's the DC circuit. Because this isn't open, we can take this whole portion out. I was already drawing the AC circuit. I was trying to get ahead. This cap is open, so none of this exists. This cap is open. All we're left with for the DC circuit is this portion right here. And now I'll look at what somebody was talking about. Yeah, you're right. I was saying it exactly backwards. I was doing the AC version of that instead of the DC version. Okay, so we're given some information about this transistor too that we'll use later. So this is correct on here. DC capacitors are open, and I wrote that down. And so there's my DC circuit. Now I was given that ID was a 0.5 milliamp. So the only things I have left to find are VDS and VGS. Since this has no current going into it, I can use the voltage divider rule to find VG. And that's a bad color now. VG. So VG is just going to be whatever my VDD is times 200K over 200K plus 300K. And that'll come out to be 2 volts when I plug the numbers in. Now I was given ID was 0.5 milliamp. And for MOSFETs, ID and IS equal the same thing. So this is also 0.5 milliamp. So I can use Ohm's law on this R11 resistor right here. It's got the voltage at S will equal whatever the current is times RS, because the other end of the resistor is grounded. In this case, if it was tied to a negative source, then this equation wouldn't be quite right. 0.5 milli times 2K gives me 1 volt. So I've got VS, I've got VG. We can use Ohm's law again to find the current right here, VD. This is the source, that's the drain. It would be VDD minus VS would give you 0.5 milli times 5K. I rearrange that a little bit and I get this equation, and that comes out to be 2.5 volts. So now once I know VD, VG, and VS, I can calculate VGS. It's just VG minus VS, 1 volt. VDS is VD minus VS is 1.5 volts. We've got our DC operating point. Okay. And then next step was to calculate GM and RO. Well, I go and I look at what I have. I wasn't given, was I given KN? I was given KN, but anyways, I can use any version of that equation that I have information of. There's 4 different versions. The one I used right here, this 2ID over V over voltage. And V over voltage is VGS minus VT. So I plug in what I have, and I get 2.5 millimos. That would be milliamps per volt. Be another unit for it. In Mohs, it kind of reminds you it's a conductance, and I can flip it over and turn it into a resistor. We'll do that in 380. RO, I was given VA. The other version of this equation, of course, is 1 over lambda ID. If I was giving lambda, I would have to use that one. I calculate RO, 200 volts was my VA, divided by 0.5 milli. It's 400 K ohms, which is about in the right ballpark. So those are the different forms of the equation for GM and RO down there. Slide 24, sure. And let's get rid of that so you can see it. Okay. Okay, no problem. And then we got that. So now that we've got GM and RO, we can plug them in here. We did have a value for GM. Our RO was 400 k ohms. This is the model of the transistor minus the ground. That's a small signal model. We got a value for GM, 2.5 milli. And we look at the circuit to see what's connected where. Now this is the AC circuit. Let's see if I can get this right this time. The capacitors are shorts. This is what I was trying to say before. This is what I wrote down before. The DC voltage supplies are going to be shorted out. And the AC voltage supply, the DC current supplies, probably won't get one of those, are going to be open. So I short out my capacitor. I short out all the capacitors. I take the DC voltages and I short them to ground. So I get rid of that. Short this to ground. And that is pretty much my circuit. Now I've got to take this model that I've got down here and I've got to fill in where things on the circuit are connected. Did I miss the source resistor? Yeah, I did. Oh, no, I didn't. Because on the source, you've got a short in parallel with a 2 k ohm resistor. That is going to be a short to ground. So my source here gets grounded. That is correct. The drain right here, what I see is 5 k to ground, and the capacitors are short in parallel with 5 k to ground. So there's my two 5 k ohm resistors, and this is the output voltage right there. And on the gate, I see 200 k to ground, so that's this one. I see a 300 k resistor to an AC ground, so those two are effectively in parallel. And also tied directly to the gate, I have 120 k to my input source. So that is the AC circuit. This is so much easier. This is easier than doing it on the board. I'm lazy, I'm not drawing enough. So in order to analyze that AC circuit, I'm gonna like draw this line through here and treat it like it's two different circuits. So this is tied to ground, this is tied to ground, this is tied to ground. These are all tied together. The input part of this, what I want to calculate is VGS over VN. It's a voltage divider. So VGS over my input voltage, and I called it V sig in the equation. It's the parallel combination of this 200K and 300K divided by that resistor right there, the sum of the two resistors. And that comes out to be 0.5. When I look at the second part of the circuit over here, I have a current source going into the parallel combination of three resistors. The value of the current source is 2.5. My output is positive in this direction. The current's going into the negative terminal. So we have a passive sign convention violation, which is where the negative sign comes from. I'm solving for, it would just be, this is V equals IR. So it'd be V out equals this current source times the parallel combination of the resistors. Then I did the thing where I just divided by VGS and got the VGS out of the equation. Then I have negative 6.21. I multiply the two together, I get negative 0.3, negative 3.11. Two different circuits, and this is something we'll use a good bit in 380, but we do in 380, this is called a common source amplifier. And 380 will look at the common source, the common drain, the common emitter. Oh, wait, I'm getting way off here. Common source, common drain, common gate, a couple of two-stage amplifiers, a cascode, and we'll also look at a differential amplifier. And we'll do all these for circuits for all of them. I'll show you tricks and shortcuts to get through it. It's okay. There's a lot on this slide. We're moving over to BJTs. Let's just take a minute. Yay. Pretty much everything I use to solve every BJT problem, other than like Ohm's law and things like that in KCL, is on the slide. That says 3 main equations, but I added a 4th. Beta is defined as IC over IB. If I give you beta, you know one of those currents, you know the other one. IC can also be found by this I as e to the VBE over VT. Alpha is beta over beta plus 1, and alpha is defined as being IC over IE. And KCL tells us that IE equals IC plus IB. That's just a KCL equation. Now, if I tell you that it's an active mode, that means you assume for your hand calculations that VBE is 0.7. The first thing you write down on the transistor model. It's the only way to solve these without getting into iterative techniques that you don't want to do. If I tell you that the transistor's in saturation, then you know that VBE is 0.7 volts and VCE is 0.2 volts. And we've only dealt with NPN transistors in here. It has a cousin, it's called the PNP. But it's not used as much. It's slower and it's slower. When we're trying to calculate the values for the model, the basic ones for this one are GM and R pi. GM is IC over VT. VT, it's written on the front of your amp. It's 25.9 millivolts. And R pi is VT over IB. So that's how you calculate those. And the model, it's called the hybrid pi model because it kind of looks like an upside down pi. R pi goes between the base and the emitter, and GM goes right about there. So a different model we've got here. I think I just asked you to do DC biasing on the BJT, in which case this slide's really important. This is how you get the DC operating point. So we've got our last problem of the day, and then I'll open it up for questions. We're given beta. That's a good thing to know. We assume that it's in active mode. So as soon as I see that, I say VBE equals 0.7 volts. And I draw it on the schematic. This is the base, this is the emitter, and this is the collector. So I've got 0.7 of a volt right across there. And what can I find just by knowing VB is 0.7? Well, the emitter's grounded. The base has to be 0.7 of a volt above that. So this is going to be 0.7 volts. Once I got that, I have one side of a resistor. I've got the other side of the resistor's voltage. I can use Ohm's law, my favorite, to calculate. So the voltage drop is 2 minus 0.7, and that will equal I don't know what I is yet, IB, times R, and R is 100K. Why did I shut my notebook? I really think I was that far. Oh, great. It's in the white pages. Oh, I should know that. It is 1.3 milli, 0.1 milli, 0.13 milli, 0.013 milli, 13 microamps. I can do that. Let me get the number here. What the heck was that? IB is 13 microamps. That's what I just said. Okay, so we've got IB. The equation, the only thing I've used so far is that it's active VBE equals 0.7 volts. And then I used Ohm's law. I'm going to use this equation also. IC equals beta IB, because we have IB. So that was IB. IC, we're given beta, 100 IB. So 100 times 13 microamps is 1300 microamps, which is 1.3 milliamps. So we've got IC, we'll need that one. We might as well go ahead and, oh, we can use KCL. Our KCL equation is the sum of the currents. IB plus IC equals IE. That was one of the 4 equations I just pointed out to you. We've already used 2 of them and this little factoid. So IE is the sum of those 2. It will be 1.31 milliamps. Not much higher. Oh, what else can we get off of here? We can get VC. Did I even do that? Yeah, I did. Now that I've got the collector current, I can find the collector voltage. VCC minus VC equals IC RC. We can solve that for VC, and we can get, we got numbers for all that. This comes out to be 2 volts. We've got the base voltage is 0.7, the emitter voltage is 0, it's grounded. We've pretty much nailed that. There's our DC operating point. Probably the big thing you have to be able to do. All of that stuff is on the previous slide. All the information I ever use for BJTs is on that previous slide. Now we want to calculate GM and R pi. And GM and R naught, where am I at? We want to calculate GM and R pi, and we've done that. Where's our GM and R pi, the little thingy? Oh, there it is right there. GM's IC over VT. We've got IC. R pi is VT over IB. We found IB. We can just plug those in. GM is 1.3 milli over 25.9 milli. And it is 50.2 millimos. And R pi is VT over IB. So 25.9 milli over 13 micro. And this comes out to be 1.99 k ohms. We have to draw the AC circuit. Oh, great. This is a long class. We got a lot of stuff in here. Start with the basic circuit. R pi, 1.99 k. This is the base. This is the emitter. And then I've got the dependent source. And this is GM-VBE. And GM in this case was 50.2. We have to, and this is the collector. We're doing an AC model of this. 100K to an AC ground is on the base. Oh. $100K. And in this case, VN goes directly into that node. It's tied directly into the base. The emitter's grounded, and this sees 2 resistors in parallel. 10K in parallel with 2K. So we could go through and calculate the gain for that. We're lucky here. My input voltage is tied directly to the base. The emitter's tied directly to ground. So in this case, VN equals VBE. And I have this current source is going to ground. That's also going to ground. So these are connected together. My Vout is here. So what I'm going to get there is the current source is 50.2 milli. It's going times VBE. I'm good, I'm not frozen. Times VBE. That current source is going in the wrong direction. So there's a negative sign. 10K in parallel. Did I freeze? My little thingy's frozen. Oh, try this. No. Try the other button. Oh, I am frozen. Okay, so now I'm frozen. So it's just negative 50.2, 10K in parallel times VBE. The gain is negative 50.2 milli times 10K in parallel with 2K. And that comes out to be negative 83.7. And it's a lot neater in my slide solutions if you want to refer back to that. I'll be back in a minute. I'm glad this didn't happen last week because I tried to